Hello everyone, welcome to 𝐂𝐤𝐬𝐿. So today we are discussing about compiler design parsing concept. Today is our lecture number 6. Welcome all of you to the 𝐂𝐤𝐿 English channel and welcome to compiler design subject. So in our last class we have discussed something related to parsing, especially on bottom up parsing. Hi, how are you? Welcome to parsing. So in our last lecture, we were discussing about bottom up parsing. In today's lecture also, we'll continue the bottom up parsing because bottom up parser is the most powerful parser compared to top down parser. So the construction also little bit lengthier one here, right? Before going to start our today's session, let us see what we have discussed from bottom up parsing. Just let us recap what we have discussed in our previous class. In the previous class, we just introduced what is bottom-up parsing, how a bottom-up parsing is performed. So we were in the discussion of bottom-up parsing. So what is bottom-up parsing? A bottom-up parser constructs parse tree. A bottom-up parser constructs parse tree, starts at the string, proceeds towards starting symbol. That is bottom to top construction is happening. That is what we have discussed already. And what is the derivation used in bottom up parsing? Bottom up parser uses rightmost derivation in reverse order. Bottom up parser uses rightmost derivation in reverse order. This is the derivation used in the bottom up parsing. And next one is bottom up parser is a more powerful one. And while doing this bottom up parsing concept, we come across with a terminology called as handle. The main concept of bottom up parsing is handle detection. The major concept of bottom up parsing is detection of handle. At every step, handle is detected, handle is replaced by non-terminal. Handle concept is the major concept in our bottom up parsing. Okay, right. And then we discussed about shift reduce parsing. So if you want to perform bottom up parsing in a systematic way by using a program, that program name is called as shift reduce parsing. Shift reduce parsing. So what is shift reduce parsing? Shift reduce parsing is performing bottom up parsing in a systematic way by using program. That program uses mainly 4 operations: shift operation, reduce operation, we can say operation or action, accept, error. So we can say shift action, reduce action, accept action, error action. Like this, by using these 4 actions, performing parsing is called as shift reduce parsing. Right. So this is what we have discussed in the last class. And today we are going to discuss about the more generalized form of shift reduce parsing, LR parsing. This is practically used in the present compilers. LR parsing and LR0 items, LR0 items DFA, LR0 parsing table construction. So these are the topics we are going to discuss. So in our today's lecture, mainly we are focusing on LR0 things. What is LR0 item? What is LR0 grammars? What is LR0 items DFA? What is LR0 parsing table? Mostly on this, completely on LR parsing methods. Okay, right. So let us see what we have discussed about shift reduce parsing in the last class. So I think this diagram is, so this is our LR parser, LR0. Our discussion is today on LR0. Next SLR1, all this. We are in the bottom up parsing side. We are designing a bottom up parser. To design a bottom up parser, this is the most powerful parser. Bottom-up parser is the most powerful parser among all the parsers. So out of top, down and bottom up, this is a powerful one. In that, LR is the best one and practically used by many compilers. Most of the compilers used is LR parsers. Right. So we discussed about shift reduce parsing. In the last class, we discussed about shift reduce parsing. What is the shift reduce parsing? Handle detection concept. Whatever the handle detection concept we are using, this handle detection concept. So bottom up parsing is performed with the help of handle detection. At every step, handle is detected, replaced by non-terminal. Handle is detected, replaced by non-terminal. That is called as reduce. So this total concept, if you write in a program wise, that program is called as shift reduce parsing. So the shift reduce parsing having this shift actions, reduce actions, accept, error. We know the meaning of shift. Input buffer, moving symbols from input buffer into the stack. Shift action. If a handle is detected, replaced by non-terminal, that is called as reduce action. Majority of the actions are shift reduce actions. Shift, handle, reduce. Shift, there is a handle, reduce. This is whenever successful passing, accept action is called error action. But whenever we are doing shift reduce passing, look at here, I am performing simply, yesterday we have seen this. Whenever we are performing shift reduce parsing, we will face one problem. That is conflicts. See here, I am performing shift here in the first step. Shift, there is a handle, reduce. Then shift, there is a handle, reduce. In this case, sometimes if it is a normal shift reduce parser, the problem is, look at this. This is our grammar production we have taken already. The normal shift reduce parser for which there is a possibility of falling into conflicts, confusion, multiple possibilities. Look at this. This is the handle. This is a substring matching right hand side. So we can call this is a handle. So I can reduce. Whenever handle is there, the parser, what we have to, the main concept of bottom up parsing is, if handle is there, reduce. So reduce we can do. Shift also we can do. Here, look at here. In this, I am giving priority for shift. So when to do shift action, when to do reduce action, when you have to perform shift, when you have to perform reduce, that deciding is the major factor. In order to decide this, there is no mechanism in normal shift reduce parser. So that's why normal shift reduce parsers will generally get conflicts, that is confusions. Conflict in the sense, confusion. Normal confusion is, now the situation, both possibilities are there. I can reduce, I can shift. Which one to take, which one to perform? That decision becomes very much complex for the normal shift reduce parser. To avoid this, we are going for LR parser. So LR parsing, in which we have particular mechanism, we have particular strategy in order to handle these things. So how this LR parsers looks like? That's when bottom up parsers we have two things. So this is normal structure of LR parser. I will tell you the perfect one. This is. In bottom up parsing, we have two algorithms. One is LR parsing, operator distance parsing. So in today's class, our focus is on, we are discussing about LR parsing. Look at the LR parsing. LR parsing also shift reduce parsing. So we have all the tokens. All the tokens will be taken here in the input buffer. This is input buffer. All the tokens are taken in the input buffer along with $as end marker. In order to identify handles, we are using stack data structure. We have a stack here. Now we'll perform shift reduce thing. We'll shift symbols into the stack. we'll check for handles. Now assume there is a handle. There is a handle. Now two possibilities. I can reduce, I can shift. Which one? Which one I have to do? For which I have to give priority. In order to decide this, till this up to this part, it is shift reduce parsing. But in order to take decision regarding, so we have a guide, or there is something called as table that is giving proper guidance to our normal shift reduce parser. So attaching like this table to the normal shift reduce parser, this total structure is called as LR parsing. So LR parsing also simple shift reduce parsing. So what is the major difference? In normal shift reduce parsing, we don't have these tables. That's why confusion to the parser. Now what happens? What decisions it has to take? Shift or reduce. Every time parser comes to the table. Look at the table here. Table having S indicates shift, R indicates reduce, shift, reduce, accept. All this blank indicates errors. So all these blank errors. Like this, table gives the perfect information. So these tables are called as LR parsing tables. So LR parsing is not a new one. LR parsing is shift reduce parsing. What is the difference in normal shift reduce parsing? In normal shift reduce parsing, in order to take decision regarding shift and reduce, when to perform shift, when to perform reduce, sometimes even the handles are there, we will perform shift. How to know that? That information, that decision is given by this table. That's why these tables attaching to the shift reduce parser, then this whole structure is called as LR parser. So LR parser is a simply shift reduce parser and having one tables in order to take decision regarding shift and reduce. That's what LR parsing. So in LR parsing, if you want the meaning of L is nothing but left to right scan of input, so left to right scan of input. Here R indicates rightmost derivation, using rightmost derivation in reverse order. Using rightmost derivation in reverse order. So like this, the LR parser is a shift reduce parser having one additional table. The table is the main concept here. That's why if you want to perform any LR parsing, so what we have to do, how these tables are constructed for corresponding to the given grammars, we have to prepare this table, we have to design this table. So once design this table, attach this to the shift reduce parser, then shift reduce parser is doing parsing, then it will say the syntax is valid or not. So output of this will be for valid input parsed. Okay, so now in today's class, let us focus on how to design these tables. If the table is there, then only we can attach this and parsing is running total LR parsing. Okay, is it clear up to this? Is it clear for everyone? So in today's class, our aim is designing of this table. Name of the table is LR parsing table. Just observe the table. I'm just giving you time to observe this table, how this table looks like. So the table is generally is of two parts. This is called as action. Here shift actions, reduce actions information is there, and the columns are terminals plus dollar here. All the non-terminals are this side. and this is called as goto table here. So we have to prepare this table now. So here shift actions reduce accept error here states, and this table is designed by using some DFA, deterministic finite automata. So for the given grammars, all these things we are going to discuss now, how we can construct this table for the given grammars. Right. To design these tables, in order to design the tables like this, we have different techniques. To design these tables, we have different techniques called as, first one is LR0 parser. If you design a table by using LR0 method and attaching the table, that is called as LR0 parser. Next one, SLR1 parser. Next we can say LR1 parser, that is also called as CLR1 parser. Next one more thing is called as LALR1 parser. So in order to design these tables, we have four techniques, four methods here: LR0, SLR1, CLR1, LALR1. So LR0 is the most easiest one, very easy one. So almost all these tables, all these four techniques are there in order to design table. Previous table, whatever I have shown, in order to design this table, we have these many techniques, four techniques. Almost all same. The construction of table is, today's class we are learning about LR0. For SLR, CLR, LLR, almost all same. Small changes are there. Okay. So on grammars, working on small class of grammar, few number of states, hence very small table, simple and fast construction happens. In LR0, SLR almost same. Okay. And CLR works on complete set of LR1. Grammar generates large table and large number of states, slow construction, because very large tables are there, construction takes a lot of time. Works on intermediate size of grammar, number of states are same as in SLR. Okay, right. So let us focus on. So can you tell me, to design these tables, how many methods are there? How many methods? To design the table, how many methods are there? So there is a algorithm. See, we have top down parsing algorithms, bottom up parsing algorithms. LR parsing algorithm, total algorithm time complexity order of n. Some student asking what is time complexity for order of n cube. We have a parsing called as CYK parsing. CYK parsing, that is a used in very olden days. Nowadays they are no one is using that, but that is taking order of n cube. N cube is taken by CYK parsing. Okay, but algorithm is there. Parsing one of the algorithm, it is taking order of n cube. Algorithm is okay. Let us go and study LR0. See, LR0 table construction is an algorithm, systematic procedure. Here also we have systematic procedure. So these are the steps. If you want to construct LR0 parsing table for any grammar, first for the given grammars, see, grammars are converted into tables, are nothing but grammars. Whatever the grammars are there, grammars are converted into tables. Okay. So if any grammar is given, first we need to construct augmented grammar. So if any grammar is given, construct the augmented grammar. First one. There are three steps to construct table. To construct whatever the previous table shown, no, Nella, to construct this, first we need to construct augmented. I'll explain what is augmented grammar and everything. Second one, construct LR0 items DFA by using closure and goto. This is also called as construct a set of set of LR0 items, or we can say canonical collection of LR0 items. So second step is very, very important here. This is the most important step. Once you understand this, it's very easy. The main concept of this table construction is there in the construction of LR0 items DFA, or construction of set of LR0 items, or canonical collection of LR0 items. All the names are same. Construct canonical collection of LR0 items. I'll explain the meaning, but first listen this. Then construct the once this is this is there with us. Construction of parsing table is very easy. Okay, right. So let us see what is this. First, what is the augmented grammar? See, normally every parsing table is converted into whatever the parsing table is there. The parsing table is nothing but grammars. Given grammars generally converted into parsing tables. So first, what is the augmented grammar? The first one, we'll focus on the first one here. Here we have to see what is the meaning of augmented grammar. Augmented grammar. So what is the augmented grammar? So if we have a grammar like this, if we have a grammar like this, just constructing, adding a new production, S dash gives S. For this one, this total structure is called as augmented. So this is the original production. This is the given grammar productions. Adding a new production like S dash gives S. Now this total grammar is called as augmented grammar. What is the advantage? We have something called as accept action. You come to know while constructing the table, we'll get the accept actions because of this one. So in order to get the accept action after successful completion of parsing, to get the accept action, so we need to add one extra production. This production is not actually there in the grammar. The original grammar is this much only. Original grammar is this much. So what is this starting symbol of the grammar? We are bringing forcibly to the right side and adding a new production. S dash a new non-terminal. S dash gives S. Adding like this, new one, new production to the original grammar production. This total structure is called as augmented grammar. This is our augmented grammar. Okay. This is our first point. This is very easy. So construction of augmented grammar is the first one. Second one, compute LR0 items. Construct LR0 items DFA, or compute set of LR0 items, or canonical collection of LR0 item. First of all, let us know what is this LR0 item. There is a difference between normal grammar production here. These bottom-up parsings are guided through some special dots. This is a grammar having three productions. This is the first production. So grammar productions are completely different from LR0 items. What is this LR0 item? LR0 item is nothing but parser is guided by using particular way, using some dot. So normally if the production is like this, just without dot, that is called as grammar production. Whenever we put a dot in right hand side of the grammar, this is called as LR0 item. This is a special way of notation in bottom up parser, to LR parser. Okay. So this is LR0 item without dot. Dot is not there. Grammar production. Put the dot. LR0 item. Where we can put the dot? Anywhere in the right side. We'll start from here. Sometime we can put here. Sometime we can put here. That is also LR0 item. Sometime we can put a here. That is also LR0 item. So these LR0 items gives the particular meaning for us. Okay. So these are some of the possible LR0 items. Corresponding to given grammar production. So dot can be placed here, dot can be placed here, dot can be placed here, anywhere at only one position. These are called as LR0 item. So this is also one of the LR0 item. This is also one of the LR0 item. So these LR0 items, understood the concept of this? LR0 item gives particular meaning to the parser. Whenever you have any LR0 item is like this. This is one LR0 item. It gives particular meaning to the parser. So this dot, whatever is dot left part, whatever is there, parser has seen this part already. It has to see this part. So dot left part is already there in the stack, already entered into the stack, and it is read by the parser. Dot left part. Right part is parser is ready to see. This particular indication will be given. That's why in a systematic way parser, all these things are to identify handles properly, to identify. So it will take the dot, it will move the dot one position ahead, and it will see. So many things are there. In the construction you come to know. Whatever it may be, LR0 item is completely different from grammar production. So LR0 item is having dot somewhere in the grammar right hand side part. These things are called as LR0 items. So the collection of these LR0 items is our main concept. Based on these LR0 items, once you compute these LR0 items, we'll construct a DFA, that is LR0 items DFA. That DFA, based on that, we'll construct a table. So in the table we have seen I0, all these are states, DFA states. So like this, based on states and based on these LR0 items, we can construct a complete parsing table. Okay. This is what the meaning of LR0 item. Next we will go for function called as closure. So to compute these LR0 items, to calculate these LR0 items, how many LR0 items, how many states of the DFA, all these things, if you want to compute, we want the help of two things: closure and goto. Closure and goto are two functions here. Closure and goto are two functions. They are doing some particular task. Closure is doing some particular task, closure function. Goto function is doing some particular task. So by using closure and goto only, total number of LR0 items, total number of states of the DFA, LR0 items DFA, we are calculating. What this closure is doing here? So for any LR0 item, assume my grammar is this way. This is the grammar. For this, what the closure will do is, in any LR0 item, after dot, a non-terminal exists. After dot, a non-terminal exists. Then closure function. So we have in some state like this. After dot, a non-terminal is there. Closure is adding that non-terminal production. Closure is adding that non-terminal production. That is what the, so what is this? After dot, capital A is there. So closure, the task of closure is just add this and convert into LR0 item by putting the dot in the first position. That's all. This is the concept of closure. So assume in some of my state, I have something like this. This is the question asked many time in GATE paper, including last year also. Closure function is very important. So assume I have some item like this, LR0 item. After dot B is there. What closure will do? Tell me. What closure will do? Closure function is doing particular task. Here closure and goto are two functions. They are doing particular task. What the closure function is doing? What the closure is doing? Yes. After dot B is there, no? So I'm just giving time for you to recollect this. B production, whatever is there, after dot capital B is there. B production, it is adding B production. This is the task of closure. Add this production and place the dot in the first place. In anywhere, we have the closure function is like this. Okay. Even if you have some other thing, then after dot, how many non-terminals? All their things will be added. This is closure. Closure is that's all. So closure function. Then we have something called as goto. This is a small goto actually. Goto function. Goto. What is this goto is doing? Assume we have some LR0 item like this. If we call goto function, goto is moving dot one position towards right side. One position towards right side. This is the task of goto. That's all. So goto, what it is doing? Moving the dot one position towards right side. So if I apply goto on this item, whatever the dot is there, moving this side. That's all. This is goto. So in any LR0 item, assume I have like this. This is some LR0 item. If I apply goto on this, if we apply goto on this dot is moving something towards right side. So this dot is moving right side. So this is the concept of goto. Like this, that's all. So if you know closure and goto, closure is adding productions. Goto is moving dots. So with the help of this closure and goto, we will construct total number of LR0 items. Total number of LR0 items possible corresponding to the given production. Okay. Given grammar productions. Right. So then construction of table is the last one. We'll see that later. Now we'll practice through some example how to implement first and second steps in the algorithm. So if a grammar is given, how to construct an augmented grammar and how to construct the total set of LR0 items and how to construct the LR0 items TFA. Okay, right. So let us study this through some example. This is one of the grammar. So let me write this grammar here. That will be easy for us. Now we have to construct. Question is construct LR0 parsing table for this grammar. So we have to construct LR0 parsing table for this grammar. For that, what is the first step here? What is the step 1 from our algorithm? Step 1, augmented grammar. Augmented grammar. So can you tell me how to construct the augmented grammar? How to construct the augmented grammar? Just by adding new production, S dash to S. If you do this, our step 1 is completed. Just by adding a new production S dash to S. Augmented grammar. Is it clear? So the augmented grammar construction very simple. Whatever the starting symbol is there, by taking the starting symbol into the right side, construct S dash to S. This is augmented grammar. Next we are constructing for LR0 items DFA. Construct LR0 items DFA. So I am constructing directly LR0 items DFA here. LR0 items DFA. So what we have to do here, look at the construction of LR0 items. First take the augmented grammar, augmented production. So this is the DFA, directly constructing DFA. Now the initial state 0 of the DFA is like this. First to take the augmented production and convert into LR0 item by placing the dot. Augmented production, place the dot. That's all, that much we are doing intentionally. After that, closure and goto will handle. Everything will be designed by closure and goto. Now tell me, is there any closure possibility now? Is there any closure possibility? After dot, whenever non-terminal is there. Yes, closure. What the closure will do? Adding S production. Adding S production. And placing the dot in the first place. Closure again will be continued. Yes, again closure is there. What is the closure? After dot, whenever we have A production is added. A production is added and placing the dot in the first position. Placing the dot here. So closure will do all these things. Now B production will not be added because not added into the state, because after dot immediately capital B is not there. Okay. So like this is the first what we have to do. State 0, initial state of the DFA is constructed. A production is added. Do you need to add the B production here? In the state 0, first state, do you need to add the B production? We are not doing anything intentionally. This is algorithm. That too, that is done by a closure function. So when closure function will add, it will add a production. Whenever dot followed by non-terminal exists. Here it is not there. No need to add the B production here. That's all. At I0 state, take an augmented production, applied closure. The closure is resulting this. Right. Then go to. Okay. So apply goto. On every item we'll apply goto. So the goto on this. Whenever you apply goto on this, it is resulting some state like this. Dot is moving this side. So we can give a name for this as I1. Right. And we apply the goto on this. And it results like this. And we apply the goto on this. It results like this. Goto, what it is doing? Just moving dot one position towards right side. So the names for this is I2 and this is I3. So on every item apply goto. The goto on first item, this one. Goto on the second item, this one. Goto on the third item, one state. So all these are states of this DFA. This is the DFA, states of this DFA. Okay. Right. So we can take on A, on whatever the symbol, that symbol also it is on capital A. Symbols, dot on this symbol, like this, on capital S. Like this also we can say. Okay, right. So now I0 state, closure on every item, closure on every LR0 item, goto on every LR0 item, goto on every LR0 item is completed. So closure on every LR0 item, goto on every LR0 item is completed. Now let us come to the I1 state. I1 state. Like this, go to every state, closure and goto we have to check. In I1 state, any closure and goto possibility? Is there any closure and goto possibility? In I1 state, do you have any closure and goto possibility? So closure is not there. After dot next, right side next, nothing. Closure is not there. Goto also not there. I1 perfect. I1 possibilities are closed. Then let us go to the I2. Any closure? Yes. After dot B is there. What the closure will do? Add B production. Add B production and place the dot. Okay. Then apply goto. In I2 closure and goto we have to complete. So goto on this. So this is completely moving. Goto on this. So if we use the goto on this one as well as goto on, if we say capital B, this is a goto on small b. So I2 state, closure completed, goto on every LR0 item completed. I3 state, any closure and goto on I3 state? In I3 state, it's already dotted rightmost end, no closure, no goto. Now we can give the names as this is I4 state, this is I5 state. Any closure and goto on I4, I5 states? I4 state, closure is completed, no closure possibility. Goto is completed, no goto possibility. So I4 state, no closure, no goto. I5 state, no closure, no goto. That's all. This is the DFA. That's all. If whenever a grammar is given, we should be in a position to construct this. So these are our states. In the parsing table, we can see the parsing table here. Look at this. This is our table, parsing table. In this parsing table, okay. In this parsing table, all these are states. All these are states. States of DFA. All these are states of DFA. And these are, okay. How we will get these states? Like this. So how many states total? I0 to I5. Total 6 states. Look at this table. I0 to I5, 6 states. In any, if it is LR0, SLR, CLR, LALR, the rows of this table, number of rows of this table is nothing but number of states of the DFA. That's why number of rows, of table, parsing table is equal to LR0 items DFA states. LR0 DFA states. How many states are coming in the DFA? Those many states will get. Is it clear? So the DFA is the main thing. Then all these things, shift, reduce and everything is very easy once if we are able to construct this one. Size of the table is simply states this side, rows. These are terminals plus dollar, and plus all the non-terminals. So look at this, non-terminals here, terminals plus dollar here, all the non-terminals here. This structure is called as action table. This structure is called as goto table. So non-terminals plus terminals plus dollar. If you want size of the table is nothing but non-terminals plus terminals plus dollar multiplied with states. Number of states multiplied with non-terminals plus terminals plus dollar. Is it clear? So what you need to learn initially is whenever a grammar is given, so we should be in a position to construct this type of DFA. Once the DFA is ready, the table, converting DFA into table is very, very easy. So is it clear? Whenever a grammar is given, what is this table construction? The table construction also very simple thing. So we are just using closure and goto concept. Okay. So let us practice for one more example how to construct this DFA. If a grammar is given, whenever grammars are given like this, converting the grammars into like this DFA, the name of the DFA, LR0 items DFA. Constructing LR0 items DFA for the given grammar productions. Shall we practice one more of similar kind? How to construct this? Once it is constructed, the table construction is very easy. That's what I'll tell you how to construct the table. First, let us practice one more example of how to construct the DFA, LR0 items DFA. This is the actual given grammar. Okay. So what is the first step? The first step here is construct augmented grammar. First one, augmented grammar, E dash to E. So what is the starting symbol of this grammar? E. Whatever is there in the first position, that is starting symbol. That's why this one. Right. So next one, let us try to construct LR0 items DFA. Second step, LR0 items DFA construction. LR0 items DFA. Okay, right. Start from the state 0. First take the augmented one. It's very easy one. First you take the augmented production, place the dot. This is what we have to do intentionally. This is what we are doing by our own. After that, everything is done by closure and goto. Now tell me, closure function, if any item like this, closure function add what productions? How many productions? In any state, if you have this item like this, how many productions closure function will add to this from the given grammar? How many productions closure function will add to this? So whenever we say like this, dot after dot E, first closure will add E production. All the E productions. E is having 2 productions here, all this. And then it plays dot, it will convert them into LR0 item by placing the dot. Again closure possibility is there. After dot T is there. So it has to add the T production as well. So closure is adding three things. on whenever I apply closure on this, it is adding this. So there are so many questions of this kind in GATE. If you apply closure on this, how many productions are added? The total number of LR0 items after adding this. These are so many questions of this kind. So this is one of the main thing. Next, on this is I0 state. Assume it is the initial state. Now you apply goto on this. This is LR0 items DFA. Whenever you apply goto on capital E, this is moving to a state. We can say it is some I1 state. See here, whenever you are doing, it is a LR0 items DFA. After dot, how many similar non-terminals are terminals? All the same non-terminals will be moving to the same state. Yes, for goto on T, we have to we have only one thing. So on this, after dot T, so both will be going in the same state. This is LR0 items DFA I am saying. So multiple states it will not go. Dot followed by how many T's are there? Both you have to move in the same state. Here most of the students will make the mistake here. Don't do that mistake. So just move them in the similar state. Okay. Then on small I, on this if you apply goto, so this is moving here. So that's what I am saying. So construction of this table is a major concept. Construction of this DFA like this is the main concept. Once it is there, just converting into table is very small, easy concept. Very easy concept. So designing this DFA is a main concept. Once the DFA is designed, our table is for one or two examples we will construct table. After that, without table, we will conclude every possibility of the table, because all table possibilities are there here. That's why whenever we are preparing for GATE, we have space issue also. Generally, GATE students no need to construct tables while solving questions. Table structure is not required. This DFA is sufficient. From the DFA, we can answer all possibilities. So we have to practice more on the construction of this type of DFA. Right. So this is our I1 state. This is our I2 state. This is our I3 state. So on I0, all closure and goto completed. I1, closure goto possibility not there. Come to the I2. Look at this. I2 on plus we have on plus. So the dot is moving this side. But whenever we have of this kind, again dot followed by E. E productions to be added. E productions T plus E to T, and whenever we are placing dot on this, closure will add after dot T is there, so closure is adding T also. So this is the goto of this one, right? Then on I2, closure is not there, so goto applied, closure and goto completed. On I3, no closure, no goto. Name this as I4. So let us go and see the possibility on I4. On I4, on E, this is completed. So we can give name as I5. What about this? So this is the DFA. Whenever we are saying DFA, you have to follow the minimal DFA concept. So repeated states, no need to use. So look at this. Whenever we are applying on T, goto on T, it will result the same state, right? Look at this. It will result the same state. So whenever it is the same state, so no need to give the new name, just give the name as I2 only. I2 for both of this. And whenever we are applying goto on this, on I, so this is the same as I3. So just give the name as same I3. No separate state name is required here, I3. So on I4, closure and goto completed. On I5, no closure, no goto. That's all. This also result, how many states here? This is the perfect LR0 items DFA for this. How many states resulted for this? Any idea? It is there here. How many states it resulted? So number of states are very important. The total states, 6 states. I0 to 5, 6 states. Total 6 states. So like this, if any grammar is given, we should be in a position to construct. This type of DFA. This is called as LR0 items DFA. So 0 to I0, not these two are repeated states, will not be counted. I0, I1, I2, I3, I4, I5, that's all. 0 to 5, 6 states, not 8 states. It is total states of the DFA. Whenever we are constructing its table, we have to construct by using just 6 number of states. So this is common question. If any grammar is given, total how many states? How many total number of states? The number of states, once you design this, we can easily identify the total number of states present in the given LR0 items DFA. Number of states of the parsing table is equal to number of states of this DFA. That's why even if we construct the table here, the number of rows. So see here, in today's class, we are preparing this, in which the number of states detection is the main thing. In that, how to decide the number of states of the table construction. Whenever you are constructing table, first you have to decide about the states. The rows are nothing but number of states. So number of states are number of states of the DFA. That's why, look at this. Assume this is one of the table. These are the states. Assume these are the states. How to decide this? You construct, this is not for this one, just I am showing some example. So whenever you construct a DFA, how many states are resulted in that? That one is. Okay, this is for some other example, for some other grammar. But for this is for previous one. In previous one, how we decided this? DFA states are nothing but total rows of the table. Okay, right. So whenever a grammar is given, this is the way of construction of number of states. Okay. Okay, students. So in today's session, we discussed about the construction of LR0 DFA, LR0 items DFA for the given grammar productions. If any grammar is given, by using that grammar, how to construct an augmented grammar, how to construct LR0 items DFA, or that is also called as canonical collection of LR0 items, set of LR0 items. So we have taken the meaning of what is LR0 item, what is a closure function, what is a goto function. Okay. So with this we are going to stop this session here. In the next class, we'll see how to construct the parsing table. And what are the different possibilities in the parsing table, what is shift actions, how to give shift actions, how to give reduce actions, and all these things we are going to see in the next class, along with some other parsing method like SLR, CLR also. Okay students, that's all about today's class. Thank you all. We'll see in the next class about coming topic. Thank you.